Why study chemistry and anatomy and physiology? Chemistry is concerned with composition of substances and how they change in chemical reactions. The human body, food, and medications are all composed of chemicals. All anatomical structures are chemicals, and all physiological processes are based on chemical reactions. Movement, digestion, pumping of the heart, the nervous system. Water and electrolytes make up all body fluids. The mere presence of a particular collection of atoms and molecules does not confer the unique characteristics of life. Instead, these non-living chemical components must be arranged and packaged in precise ways to form a living entity. Matter is anything that occupies space and has mass, including all living and non-living things in the universe. Solids, liquids, and gases are matter. All matter is composed of elements. Mass is the amount of matter in an object. Weight, in contrast, is the effect of gravity on that mass. The more gravity exerted on a mass, the greater the weight of the mass. An astronaut has the same mass, whether on Earth or in space, but is weightless in the zero gravity of space. Chemistry studies composition, properties, and the interaction of matter. Biochemistry is biological chemistry, and it studies the physiological processes and disease. Energy is the capacity to do work and to put matter into motion. Energy does not have mass, nor does it take up space. The greater the work done, the more energy it uses up. Energy exists in two possible forms: kinetic, which is the energy of action, the energy of motion, and potential energy is stored or inactive energy. This is energy that could be used to do work but is not at the moment doing work. Energy can be transformed from potential to kinetic energy. Stored energy can be released, resulting in action. Humans store energy in chemical bonds. Elements are the simplest types of matter with certain chemical properties. There are 92 naturally occurring elements. The periodic table lists all known elements. Elements come from the environment provided by foods you eat and the air you breathe. Like all matter, both living and non-living, the human body is a combination of specific atoms, which are the smallest building blocks of matter. The most common atoms in the body, oxygen, carbon, hydrogen, and nitrogen, make up approximately 96% of the total body chemistry. These common atoms and a few others combine to form the molecules of life, such as proteins, carbohydrates, fats, and nucleic acids, which is the genetic material, such as deoxyribonucleic acid, or DNA. These important atoms and molecules are the inanimate, raw ingredients from which all living things arise. Compounds are chemical combinations of different elements joined by chemical bonds. Glucose is made up of 6 carbons, 12 hydrogens, and 6 oxygens. Water is made up of 2 hydrogens and an oxygen, and deoxyribonucleic acid is made up of many elements. This is a table of the major and trace elements of the human body. All matter is made up of tiny particles called atoms. These particles are too small to be seen individually, even with the most powerful electron microscopes available today. Atoms are the smallest particles of an element that have properties of that element. They are the unique building blocks of each element, and they give each element its particular physical and chemical properties. Each element is represented by an atomic symbol, which is 1 or 2 or sometimes 3-letter chemical shorthand for each element. For example, O represents oxygen and C represents carbon. Some symbols come from Latin names like Na for natrium, which is sodium, and K for kalium, which is potassium. Even though extremely small, atoms consist of 3 types of even smaller subatomic particles. The types of atoms vary in the number of these subatomic particles they contain. Protons are large particles, and they carry a single positive charge. Neutrons are large particles that carry no electrical charge. and electrons are small particles and they carry a signal negative charge. Atoms consist of a central nucleus, which contains protons and neutrons, and electrons in a constant motion around the nucleus. The number of protons equals the number of electrons in an atom. Therefore, atoms are electrically neutral. An atom consists of two regions, a dense central nucleus made up of protons and neutrons, surrounded by a three-dimensional electron cloud, where electrons move rapidly around the nucleus in orbitals. The magnitude of the charge of a proton exactly matches that of an electron, but it is an opposite in sign, being positive. In all atoms, the number of protons in the nucleus is equal to the number of electrons moving around the nucleus, so their charges balance, and the atoms are neutral. The atomic number is the number of protons in the nucleus of an atom of a specific element. Each element has a unique atomic number, and that number identifies an element. Regardless of where they are found, all hydrogen atoms have 1 proton in the nucleus, all carbon atoms have 6, and all oxygen atoms have 8 protons in the nucleus. These numbers also represent the number of electrons moving around each nucleus. Therefore, the number of electrons and the number of protons in an atom are equal. The number of protons in the nucleus of an element is called the atomic number of the element. In addition to an atomic number, each element also has a mass number. This is the number of protons plus the number of neutrons in one atom. Electrons do not contribute to the mass of the atom because they are so light. This is a periodic table. It gives you information about the atomic properties of the elements. They're listed in the table by their atomic number. All atoms with 1 proton are hydrogen, 2 are helium, 3 are lithium, 6 are carbon, 11 are sodium, 12 magnesium, 15 phosphorus, and so on. All atoms of a certain element have the same atomic number, that's the number of protons. Isotopes are atoms with the same atomic numbers, but with different mass numbers. Remember, mass number is the number of protons plus the number of neutrons. So isotopes contain different numbers of neutrons, but the same number of protons and electrons. Oxygen often forms isotopes, oxygen 16, 17, and 18, with the numbers representing the mass numbers. Radioactive isotopes are unstable, releasing energy or atomic fragments. This is known as atomic radiation, until they gain stability. Some are used to detect and treat disease. For any element, the atomic weight is often considered the average of the mass numbers of all its isotopes. Radioactive iodine can be used to destroy cancerous thyroid gland tissue. This is very effective because the thyroid gland is the only part of the body that actively transports and metabolizes iodine. Radioactive isotopes have many medical uses: detecting coronary blood vessel disorders, evaluating kidney function, measuring hormone concentrations in body fluids, and assessing changes in bone density. Radiation, as alpha, beta, and gamma radiation, are called ionizing radiation because its energy can remove electrons from atoms, resulting in the formation of ions. The free electrons can damage nearby atoms. Ionizing radiation sources include X-rays, naturally occurring radioactive elements in the crust of the Earth, and nuclear weapons. A molecule is the smallest unit of a pure substance that has the properties of that substance and is capable of a stable, independent existence. Molecules are formed when 2 or more atoms chemically combine, like oxygen O2 or hydrogen H2. Pure substances composed of more than one type of atom are known as compounds. Pure water, for example, is a compound that contains atoms of hydrogen and oxygen in a 2-to-1 ratio, regardless of whether the water is in the form of liquid, solid, as in ice, or vapor, as in steam. Molecular formulas are used to depict the elements present and the number of each atom present in the molecule. H2 is a molecule of hydrogen. C6H12O6 is a molecule of glucose, and H2O is a molecule of water. Solutions are usually homogeneous mixtures, meaning the particles are evenly distributed throughout the mixture. They contain a relatively large amount of one substance called the solvent. This is the substance in a solution that is present in greatest amount, usually a liquid such as water, and solutes, which are substances in a solution dissolved in the solvent and present in smaller amounts. For example, in blood sugar, glucose is a solute and the blood plasma is the solvent. True solutions are usually transparent because they are mixed evenly throughout. That's what makes them homogeneous. Most solutions in the body are true solutions of gases, liquids, and solids dissolved in water. So let's look at some examples of some mixtures. Seawater is a mixture. The solvent is water and the solute is salt, sodium chloride. Lemonade is a mixture. The solvent is water and the solutes are sugar and lemon juice. Now, we can have mixtures of gases. The air that we breathe has nitrogen as the solvent, as it is the most abundant component in the mixture. Nitrogen makes up about 78.09% of the air. The other solutes in the air include oxygen, water, and carbon dioxide. A solution is made by dissolving a solute in a solvent. The solute is added to the solvent, it dissolves, and is evenly distributed through the solvent, producing a solution. There are three main differences between mixtures and compounds. Unlike compounds, mixtures do not involve chemical bonding between components. Mixtures can be separated by physical means such as straining or filtering. Compounds can only be separated by breaking their chemical bonds. Mixtures can be heterogeneous or homogeneous, and compounds are only homogeneous. Because all matter is made up of atoms, atoms must somehow be held together to form matter. The forces holding atoms together are called chemical bonds. Chemical bonds are energy relationships between electrons of reacting atoms and not actual physical structures. They result from interactions between the electrons of atoms. Not all chemical bonds are formed in the same way, but all involve the electrons of atoms. They determine whether a chemical reaction will take place, and, if so, what type of chemical bond is formed. An atom's electrons are arranged in electron shells. This is a hydrogen atom. It has one proton and one electron. This is a helium atom. It has two protons, two neutrons, and two electrons. And this is a lithium atom. It has three protons, 4 neutrons, and 3 electrons. This is a sodium atom. It has 11 protons, 12 neutrons, and 11 protons. Electrons tend to move around the nucleus in a specific pattern. The orbitals or pathways traveled by electrons around the nucleus are arranged in an orderly series of concentric layers known as electron shells. Each electron shell can hold a specific number of electrons. The first shell, closest to the nucleus, so the innermost shell, can contain a maximum of only 2 electrons no matter what the element is. The second shell can hold a total of 8 more electrons, and the third shell can hold a maximum of 8 electrons. As the number of electrons increases with increasing atomic number, still more electrons occupy successive shells, each at a greater distance from the nucleus. Electrons of an atom occupy regions in a space called electron shells which encircle the nucleus. Electrons in the outermost or valence shell determine whether the atom will react with other atoms to form chemical bonds. For atoms with atomic numbers of 18 or less, the following rules apply. The first shell can hold up to 2 electrons. The second shell can hold up to 8 electrons, and the third shell can also hold up to 8 electrons. Lower energy shells, or the inner orbits, are filled first and are stable with a certain number of electrons in the outermost shell, 2, 8, or 18 in larger atoms. Atoms tend to undergo processes that result in a filled outer electron shell. Thus, the electrons of the outer or valence energy shell determine the bonding characteristics of an atom and its ability to interact with other atoms. Atoms that have a vacancy in their outermost shell tend to give up, accept, or share electrons with other atoms, so that all participating atoms have filled outer shells. A chemical bond is the force of attraction that holds participating atoms together as a result of an interaction between their outermost electrons. There are three major types of chemical bonds: ionic, covalent, and hydrogen bonds. An ion is an electrically charged atom that gains or loses electrons to become more stable. A cation is a positively charged ion, formed when an ion loses electrons. If you lose a negative, you're inherently more positive. I remember that cations are positive because the T in cation looks like a plus sign. Anions are negatively charged ions, formed when an atom gains an electrons. If you gain a negative, then you become more negative. Remember, anions are negative. There's two N's for negative in anion. By giving up or accepting electrons, the sodium atoms and chlorine atoms have achieved filled outer shells, but now each atom is electrically unbalanced. Although each sodium atom now has 10 electrons, it still has 11 protons in the nucleus and a net electrical charge, or valence, of +1. Similarly, each chlorine atom now has 18 electrons but only 17 protons. Thus, each chlorine atom has a -1 charge. Such charged atoms are called ions. Note that both a cation and an anion are formed whenever an electron is transferred from one atom to another. Because opposite charges attract, sodium ions and chloride ions are attracted towards each other. This electrical attraction that holds cations and anions together is known as an ionic bond. Ionic bonds hold sodium and chloride together in a compound called sodium chloride, which is common table salt. Because opposite charges attract, sodium ions, Na+, and charged chlorine ions, now called chloride ions, Cl-, are attracted toward each other. This electrical attraction that holds cations and anions together is known as an ionic bond. A sample of sodium chloride actually contains sodium and chloride ions in a three-dimensional geometric arrangement called a crystal lattice. The ions of opposite charge occupy alternate sites within the lattice. The ionic bonds make crystals form. Covalent bonds are strong chemical bonds formed between atoms that share electrons. The shared electrons actually orbit around both atoms. A carbon atom can share 4 electrons in its outer shell. 2 atoms of hydrogen can combine to form a hydrogen molecule, H2. Both atoms in the molecule become more stable because the electrons are orbiting both atoms, and it feels like each atom has 2 electrons in its outermost shell, and that feels full. Atoms like to have a full valence shell. Hydrogen molecules, H2, combine with oxygen molecules, O2, to form H2O, 2 water molecules. Notice in the water molecules, each hydrogen feels like it has 2 electrons in its outer shell, and each oxygen feels like it has 8 electrons in its outer shell. Structural formulas show how atoms bond and are arranged in various molecules. One line between atoms means that one pair of electrons are being shared. That means forming single bonds. While 2 lines indicate that 2 pairs of electrons are being shared. That's forming double bonds. And 3 lines would indicate that 3 pairs of electrons are being shared. That would indicate a triple bond. Covalent bonds are the strongest of all chemical bonds. That is, they are the hardest to break. The electrons between two atoms in a covalent bond are not always shared equally. When the atoms sharing an electron pair are identical, such as two oxygen atoms, the electrons are attracted equally by both atoms and so are shared equally. The result is a nonpolar molecule. The term nonpolar implies no difference in the two ends, or two poles, of the bond. Because both atoms within the molecule exert the same pull on the shared electrons, then each shared electron spend the same amount of time orbiting each atom. Thus, both atoms remain electrically neutral in a nonpolar molecule such as O2, oxygen. This is also true of carbon dioxide. In carbon dioxide, the electrons that are shared between the carbons and oxygen are shared equally. It results in an electrically balanced nonpolar molecule. The molecule is linear and symmetrical. Polar covalent bonds form when the electrons are not equally shared. This is found between atoms with different electronegativities. When the sharing atoms are not identical, unequal sharing of the electrons occurs because atoms of different elements do not exert the same pull on shared electrons. For example, an oxygen atom strongly attracts electrons when it is bonded to other atoms. This results in a polar molecule due to the unequal sharing of the electrons between the different types of atoms covalently bonded together. Water molecules are good examples of polar molecules. The oxygen atom pulls the shared electrons more strongly than the hydrogen atoms within the two covalent bonds. Consequently, the electron of each hydrogen atom tends to spend more time away orbiting around the oxygen atom than at home around the hydrogen atom. Because of this non-uniform distribution of electrons, the oxygen side of the water molecule, where the shared electrons spend more time, is slightly negative. The two hydrogens that are visited less frequently by the electrons are slightly more positive. Note that the entire water molecule has the same number of electrons as it has protons, so as a whole it has no net charge. This is unlike ions, which have an electron excess or deficit. Polar molecules have a balanced number of electrons and protons, but an unequal distribution of the shared electrons among the atoms making up the molecule. This results in an asymmetrical, nonlinear molecule. Hydrogen bonds are relatively weak attractions of slightly positive hydrogen ends of one polar molecule to a slightly negative nitrogen or oxygen end of a nearby polar molecule. They can form between adjacent water molecules. These act as an intramolecular bond holding a large molecule in a 3D shape, and this is important for protein and nucleic acid structure. Polar molecules are attracted to other polar molecules. In water, an attraction exists between the positive hydrogen ends of some molecules and the negative oxygen ends of others. Hydrogen is not a part of all polar molecules, but when it is covalently bonded to an atom that strongly attracts electrons to form a covalent molecule, the attraction of the positive end of the polar molecule, the hydrogen, to the negative end of another polar molecule is called a hydrogen bond. Water bugs can walk on water because of the extra intramolecular forces due to the hydrogen bonds. If you were to throw a rock into the water, it would disturb the hydrogen bonds and the bugs would sink. Whenever they sense a disturbance, they fly up in order to prevent that from happening. But then if you just wait a fraction of a second, the hydrogen bonds within the water reform, making the water strong enough that it can hold the bugs, and so they will settle back down. Chemical reactions occur when chemical bonds form, rearrange, or break between atoms, ions, or molecules. Reactants are the starting materials of a chemical reaction, the atoms, ions, or molecules. Products are substances formed at the end of the chemical reaction. Amounts of reactants and products are shown in balanced equation. Reactions are represented by equations in which the reacting substances, the reactants, are typically written on the left, and the newly produced substances, the products, are written on the right. And an arrow, meaning yields, points from the reactants to the products. A chemical equation is a chemical bookkeeping ledger that describes what happens in a reaction. The total number of atoms of each element must always be the same on the left and right sides of the equation. However, no atoms are lost. Such equations in which the same number of atoms of each type appear on both sides are called balanced equations. When writing a balanced equation, the number preceding a chemical symbol designates the number of independent or unjoined atoms, ions, or molecules of that type, whereas a number written as a subscript following a chemical symbol denotes the number of a particular atom within a molecule. The absence of a number indicates one of that particular chemical. In chemical equations, subscripts indicate how many atoms are joined by bonds, whereas a prefix means the number of unjoined atoms. So 1 hydrogen plus 1 hydrogen yields 1 hydrogen gas, H2. 4 hydrogens plus 1 carbon yields 1 methane, CH4. The types of chemical reactions include synthesis reactions, where a more complex chemical structure is formed. A plus B equals AB. This is the type of anabolism. Decomposition reactions are chemical bonds that are broken to form a simpler chemical structure. AB yields A plus B. This is catabolism. Exchange reactions are chemical bonds that are broken and new bonds that are formed. So AB plus CD equals AD plus CB. This is both anabolism and catabolism in the same reaction. A reversible reaction is when the products can change back to the reactants. And so the arrow is drawn both ways. A plus B can yield AB, and AB can yield A plus B. Under appropriate conditions, the products of a reaction can be changed back to the reactants. So all chemical reactions are theoretically reversible. Reactions that go in both directions are called reversible reactions. Often, however, conditions are such that a reaction, for all practical purposes, goes in only one direction. Such a reaction is called irreversible. For example, an irreversible reaction takes place when an explosion occurs because the products do not remain in the vicinity of the reaction site to get together to react. Many biological reactions are not very reversible. Energy requirements to go backward are too high, or the products have been removed. Chemical equilibrium occurs if neither a forward nor a reverse reaction is dominant. The forward reaction occurs at the same rate as the reverse reaction. Electrolytes are substances that release ions in water. The solution can conduct an electrical current, so it is called an electrolyte. Cations are positively charged ions, and anions are negatively charged ions. When you put sodium chloride in water, it dissolves and creates sodium Na plus ions, cations, and chloride Cl minus anions. Acids are electrolytes that dissociate to form hydrogen ions in water. They are proton or H plus donors. Hydrochloric acid, when placed in water, yields H plus hydrogen ions and Cl minus chloride ions. Bases are substances that release hydroxyl or OH negative ions that can combine with hydrogen ions. These are proton acceptors. OH negative wants to bond with H plus in order to form water. So sodium hydroxide can yield, when placed in water, Na plus a hydroxyl, OH negative. Salts are electrolytes formed by the reaction between an acid and a base. They include sodium chloride, calcium phosphates, calcium carbonate. The study of acids and bases involves measuring the hydrogen ion concentration in a solution. When an ionically bonded substance is put into water, the charged ions are attracted to the slightly charged ends of the polar water molecules. This disassociates the substance, and the ions become surrounded by water molecules. They get dissolved in the water. The substance is now called an electrolyte, since it can now carry an electrical current. So adding sodium chloride crystals to water and allowing them to dissolve separates the sodium from the chloride, so the sodiums are surrounded by water molecules, and so are the chloride. pH scale indicates the concentration of hydrogen ions in a solution. A neutral pH is a pH of 7 that indicates equal concentrations of H plus and OH negative. This is the pH of pure water. Whenever there is more H pluses than OH negative, we say that it is acidic. The pH will be less than 7 because there's a greater concentration of H pluses than OH negatives. A basic or alkaline solution has a pH that is greater than 7. That means there's a higher concentration of OH negatives than H pluses. Concentrations of acids and bases affect chemical reactions in living organisms. Hydrogen ion concentration is measured in grams per liter of body fluid, and we use a pH scale as shorthand for hydrogen ion concentration. It is based on the number of decimal places in the concentration. If hydrogen ion concentration equals 0.01 grams per liter, that's 2 decimal places, so it's a pH of 2. If hydrogen ion concentration equals 0.00000001 grams per liter, that is 9 decimal places, so that's a pH of 9. The pH scale runs from 0 through 14, and each number represents a 10-fold difference in hydrogen ion concentrations. So small changes in pH are actually huge changes because they are 10-fold. The difference between a pH of 6 and a pH of 7 is 10, and a difference between a pH of 5 and a pH of 7 is 10 times 10 or 100. And the difference between a pH of 4 and a pH of 7 is 10 times 10 times 10, which is 1,000. Acids have a pH less than 7, and bases have a pH greater than 7. A pH of 7, where hydrogen ions equal OH negatives hydroxyl ions, that is a neutral pH. So a neutral hydrogen ion concentration has a pH of 7. When there's increasing amounts of hydrogen ions, that's increasingly acidic and therefore increasingly reactive. And when there's a decreasing amount of H pluses, or you could also say an increasing amount of OH negatives, then it is increasingly basic. As it becomes more basic, it is also more reactive. Pure distilled water has a pH of 7, cow's milk 6.6, tomato juice 4.2, gastric juice in our stomach about 2. Human blood has a pH of 7.4, that's slightly basic. Egg whites are 8.0, sodium bicarbonate 8.4, milk of magnesia 10.5, and household ammonia 11.5. The things that we use to clean tend to be at the far edges of the pH scale, like ammonia and vinegar. The normal range of blood pH is 7.35 through 7.45, and you need to know that. It's going to come up often in the future, and so make sure you remember the pH of blood should be around 7.4 or between 7.35 to 7.45. Homeostatic mechanisms help regulate pH in our bodies. Buffers are chemicals which react to resist pH changes. They bind and release hydrogen ions to prevent sudden changes in pH. pH influences every physiological activity in the body. pH change interferes with cell function and may damage living tissues. Even slight change in pH can be fatal. pH affects speed of all biological and electrical reactions. For example, when the body environment is more acidic, electrical resistance lowers, hence electricity moves faster. Conversely, the more alkaline the body, the slower the electrical activity in the body. The body's pH is regulated by the kidneys, lungs, and chemical buffers. Acidemia occurs when blood pH drops to 7.0 through 7.3. Acidosis makes a person feel disoriented and fatigued. It can be caused by vomiting of alkaline intestinal contents, diabetes, lung disease with impaired carbon dioxide exhalation. Alkalemia occurs when the blood pH rises to 7.5 through 7.8. Alkalosis makes a person feel dizzy and agitated. It can be caused by high altitude breathing, vomiting of acidic stomach contents, high fever, or taking excess antacids. The original criterion used for classification was the origin of chemicals. Those that came from living or once living sources were organic, and those that came from other sources were inorganic. Today, the basis for classification is the element carbon. Organic chemicals are generally those that contain carbon and hydrogen, and they are made by living systems. Depending on the type, they dissolve in either water or organic liquids. Water-soluble organic compounds do not release ions and are non-electrolytes. They include carbohydrates, proteins, lipids, and nucleic acids. A few carbon-containing chemicals are also classified as inorganic. The most common are pure carbon in the form of diamond and graphite, carbon dioxide, carbon monoxide, and bicarbonate. But generally, inorganic compounds do not contain carbon and hydrogen. They usually dissolve in water and dissociate, forming ions, and are electrolytes. Inorganic molecules include water, oxygen, carbon dioxide, and inorganic salts. Water is the most abundant compound in living material, 2/3 of the weight of an adult human. Water is the universal solvent of life and is the major component of all body fluids. It has an important role in transporting chemicals in the body, and it is the medium for most metabolic reactions. Water absorbs and transports heat, and water balance exists when gains of water equal losses of water. An important property for any chemical in anatomy and physiology is, does it dissolve in water? If yes, it is known as hydrophilic, which means water-loving, and it would be polar. If not, then it is known as hydrophobic, or water-hating, and it would be nonpolar. If a chemical is able to dissolve in water, which means it's hydrophilic, then cell membranes can regulate its movement into and out of the cell. However, hydrophobic chemical movement is unregulated. Oxygen, or O2, is used by organelles like the mitochondria to produce energy from nutrients in order to drive cells' metabolic activities, and it is necessary for survival. Carbon dioxide, CO2, is a waste product released during metabolic reactions and must be removed from the body through exhaling. Inorganic salts are abundant in body fluids. They are sources of necessary ions like sodium, chloride, potassium, calcium, and play important roles in metabolism. They help control water concentration, pH, blood clotting, nerve, and muscle processes. Electrolyte balance exists when gains of electrolytes equal losses of electrolytes. Major organic compounds include carbohydrates, lipids, proteins, and nucleic acids. Larger organic molecules are called polymers, reflecting that they are made by the bonding together of a number of smaller subunits known as monomers. Very large organic polymers are often referred to as macromolecules, reflecting their large size. Macromolecules include many naturally occurring molecules such as DNA and structural proteins, as well as molecules that are synthetically produced, such as synthetic textiles, for example nylon, and plastics. Organic molecules that are essential for life are called biological molecules or biomolecules. Small subunits known as monomers are building blocks for the synthesis of larger biomolecules. Polysaccharides are made up of monosaccharide units linked together. Lipids, also known as hydrocarbons, are made up of CH2 or hydrocarbon units linked together. Proteins are made up of linked amino acids, and polynucleotides, which make DNA and RNA, are made up of linked nucleotide units. Carbohydrates are organic molecules of tremendous biological and commercial importance. They are widely distributed in nature and include some familiar substances, such as starch, table sugar, and cellulose. Carbohydrates have 5 important functions in living organisms. They provide energy, serve as a stored form of chemical energy, provide dietary fiber, supply carbon atoms for the synthesis of cell components, and form part of the structural elements of cells. Carbohydrates are water-soluble. They contain carbon, hydrogen, and oxygen, always in a ratio of hydrogen to oxygen close to 2:1. For example, glucose is C6H12O6. Another example would be C8H16O8 or C4H8O4. In carbohydrates, there's a ratio of carb per hydrate, C per H2O. We classify carbohydrates by size. Monosaccharides are simple sugars like glucose, fructose. Disaccharides are double sugars. That's 2 monosaccharides linked together, which include sucrose and lactose. Polysaccharides are complex carbohydrates like starch, glycogen, and cellulose. Some glucose molecules have a straight chain of carbon atoms, represented here, 6 carbon atoms in a row. But more commonly, glucose molecules form a ring structure with an oxygen linking the carbons in order to make a ring. And this shape represents the ring structure of a glucose molecule. A monosaccharide is a simple sugar. A disaccharide is 2 monosaccharides linked together, and a polysaccharide has many monosaccharides linked together. Some important polysaccharides include starch. Starch is a storage carbohydrate of plants. It consists of long, essentially unbranched chains of glucose units, which are used to form potatoes and rice. Cellulose is a structural carbohydrate of plants that exists in the form of long, unbranched chains of glucose units. The bonding between the glucose units of cellulose are slightly different from the bonding between glycogen. Humans have digestive enzymes that catalyze the breaking of the glucose to glucose bonds in starch, but lack the necessary enzymes to hydrolyze cellulose glucose to glucose bonds. Thus, starch is a food for humans, but cellulose is not. Cellulose is the indigestible fiber in our diets, and while we cannot digest it for food, it is necessary for health. Glycogen is a storage carbohydrate found in animals, so this is how we store sugar. It is a highly branched polysaccharide. Lipids are a diverse group of organic compounds made up of substances with wildly different compositions and molecular structures. Unlike carbohydrates, which are classified on the basis of their molecular structure, lipids are classified on the basis of their solubility. Lipids are insoluble in water, but soluble in nonpolar solvents like alcohol. Lipids are waxy, greasy, or oily compounds found in plants and animals, and these compounds repel water, which is a useful characteristic and can be protective like wax coatings found on some plants. Fats and oils are energy-rich and have a relatively low density. These properties account for the use of fats and oils as stored energy in plants and animals. All lipids are insoluble in water, but soluble in organic nonpolar solvents. All lipids are nonpolar. Nonpolar molecules have an even distribution of electrons. All the charges are balanced. They are neutral. Because all lipids share electrons equally, they do not want to share with polar substances, which share unequally. Nonpolar substances do not dissolve in water. They are hydrophobic, but they do dissolve in nonpolar or equally shared electron substances. Lipids include triglycerides, which commonly are called fats, phospholipids, and steroids. Lipids are an important component of cell membranes and have several functions in cells, which include storage, insulation, and protection. The most abundant lipids are triglycerides. They're used for cellular energy, contain more energy per gram than carbohydrates. They contain carbon, hydrogen, and oxygen, but less oxygen than carbohydrates, and they consist of one molecule of glycerol and 3 fatty acids. Lipids are classified as fats or oils based on their melting points. Fats are solid at room temperature, whereas oils are liquid at room temperature. This is a triglyceride. It has a glycerol molecule linked to 3 long carbohydrate chains. These are known as fatty acid chains. When the bonds between the carbons of the fatty acid chain are single bonds, they are known as saturated because each carbon is saturated with hydrogen bonds. It has all the hydrogens it can hold. But when a fatty acid chain has double bonds between the carbon, it is known as unsaturated because you could break this carbon bond by adding a hydrogen here and a hydrogen here and making it a saturated fat. Saturated fatty acids have only single carbon-carbon bonds. Most are solid at room temperature, and most are of animal origin. Unsaturated fats have one or more carbon-carbon double bonds. Most are liquid at room temperature, and most are of plant origin. Consumption of a greater proportion of saturated or unhealthy fats is linked with a higher incidence of cardiovascular disease. Phospholipids are similar to triglycerides except that they have glycerol with 2 fatty acid chains known as tails, and those tails are hydrophobic. And then they have a phosphate group that attaches at the 3rd spot of the glycerol, and this forms a polar head because phosphate is polar. The head and tail regions have different properties, making the molecules amphiphilic. The head is polar and hydrophilic, which is attracted to water, and the tails are nonpolar and hydrophobic, which is repelled by water. When you place phospholipids within water, they will automatically form a membrane. Phospholipids automatically line up with their heads facing water on either side and their hydrophobic tails hiding away in the middle. These are the main structural component of cell membranes. Steroids are also nonpolar lipids. They are made of 4 connected rings of carbon, and structurally they look quite a bit different than phospholipids and triglycerides. But because they all hate water, they are part of our lipid organic substances. Steroids are widely distributed in the body and have various functions. They are a component of cell membranes. They are used to synthesize adrenal hormones like aldosterone and cortisol, and sex hormones like testosterone, estrogen, and progesterone. Cholesterol is the main steroid in the body. Other important lipids include fat-soluble vitamins. They are vitamins A, D, E, and K. Proteins are macromolecules made up of monomers called amino acids. Proteins are the main structural component of cells, all cells, plants, animals, and enzymes, all of which are proteins, catalyze all chemical reactions in the body. Proteins are a critical component of all tissues and organs. They are used as structural materials, energy sources, hormones, receptors, enzymes, antibodies. They are built by linking amino acids together. Each amino acid contains an amino or NH2 group and a carboxyl or COOH group and a unique side chain represented by the letter R. Amino acids are bound to each other by peptide bonds. Peptide bonds form between the amine group of one amino acid and the carboxyl group of an adjacent amino acid. Because peptide bonds link proteins, sometimes proteins are referred to as polypeptides. This is the general structure of an amino acid. It has a carboxyl group and an amine group, and then an R group, which can vary. There are 20 amino acids found in the proteins of humans. This is a cysteine. This is an amino acid that has sulfur within its R group, and phenylalanine has a ringed carbon structure within its R group. From the limited pool of 20 amino acids, cells build thousands of types of proteins, each with a distinct function, in much the same way that composers create diverse music from a relatively small number of notes. Different proteins are constructed by varying the types and numbers of amino acids used and by varying the order in which they are linked together. However, proteins are not built haphazardly by randomly linking together amino acids. Every protein in the body is deliberately and precisely synthesized under the direction of the blueprint laid out in the person's genes. Thus, amino acids are assembled in a specific pattern to produce a given protein that can accomplish a particular structural or functional task in the body. The first level of protein structure is called the primary structure. It is simply the order in which amino acids are bonded together to form the protein chain. Secondary structure results when hydrogen bonding occurs between the amino acids within the protein. It will form pleats known as beta sheets in some areas of the molecule and alpha helices in other areas of the molecule. The third level of structure in proteins is the tertiary structure. It results when functional groups of amino acids react with each other. In the tertiary structure, beta sheets and alpha helices fold over on each other to form a 3D folded shape, which is also known as its conformation. And this conformation determines its function. All functional proteins exist in at least a tertiary structure. Sometimes several polypeptides interact with one another to form a fourth level of protein structure known as the quaternary structure. When two or more polypeptide chains are connected to become one protein, this occurs in hemoglobin. 4 highly folded polypeptide chains has 4 iron-containing heme groups tucked within the interior of each of the folded polypeptide subunits, and that completes the quaternary structure of hemoglobin. Shapes of protein fall into one of two categories, fibrous or globular. Fibrous are often structural proteins. They're strand-like, water-insoluble, and stable. Most have tertiary or quaternary structure in their 3D conformation. They provide mechanical support and tensile strength. Examples include keratin, elastin, collagen, which is the single most abundant protein in the body, and certain contractile fibers. Globular are often the functional proteins. They're usually compact spheres. They're water-soluble and sensitive to environmental changes. They often have tertiary or quaternary 3D conformation. Within their proper structure, they have specific functional regions known as active sites. Examples include antibodies, hormones, molecular chaperones, and enzymes. In order to stay alive, our cells need to perform the chemical reactions of life fast enough. The rates or speeds of chemical reactions are influenced by a number of factors, of which catalysts are one of the most important. A catalyst is a helper molecule that speeds up a reaction without being used up in the reaction. Living organisms use catalysts known as enzymes. They allow for millions of reactions per minute. Without the presence of the enzymes, the chemical reactions would still occur, but not quick enough to maintain life. These enzymes exert amazing influence on the rates of chemical reactions that take place in the organisms. Reactions that take weeks or even months to occur under normal laboratory conditions take place in fractions of a second under the influence of enzymes in the body. One of the fastest acting enzymes is carbonic anhydrase, which catalyzes the reaction between carbon dioxide and water to form carbonic acid. This reaction is important in the transport of carbon dioxide from tissue cells, where it is produced metabolically, to the lungs, where it is excreted. Each molecule of carbonic anhydrase catalyzes the conversion of 36 million carbon dioxide molecules per minute. Enzymes are important in essentially every chemical reaction that takes place in living organisms. So enzymes are protein catalysts. They are globular proteins that catalyze specific reactions. For each different reaction that we want to increase its rate, we need an enzyme specific for it. Enzymes regulate and increase the rates of chemical reactions. They work by lowering the activation energy necessary to start reactions. If it takes a certain amount of energy in order for the reaction to occur, the amount of time it would take to build up the energy to cause the reaction could be too long without an enzyme, but in the presence of an enzyme, the amount of energy required is much lower, so the time to build up the energy is reduced, and the reaction happens quickly. Enzymes are not consumed in the reaction, so they are used repeatedly. They are constantly recycled. Each enzyme is specific to a particular substrate. The ability to recognize substrate depends on the shape of the active site of an enzyme, which is why the 3D conformation of enzymes is so important. Many enzymes are named after substrate, with ase as a suffix. For example, lipase breaks down lipids. Lactase breaks down lactose. This is an enzyme molecule, and due to its 3D shape, it can fit particular specific substrate molecules. Once both substrates are bound, they are held in a position that takes very little energy to cause the reaction to occur. So the steps involved in enzyme action are: first, the substrate binds to enzyme's active site and temporarily forms an enzyme-substrate complex. The complex undergoes rearrangement of substrate, resulting in a final product, and then the product is released from the enzyme. Notice that the arrows of this chemical reaction go both ways. So an enzyme can take a substrate and produce a product, but it could also take the product and produce a substrate. If we want the chemical reaction to go in one direction only, then we would need to remove the product quickly away from the enzyme so that it is not available to reverse the reaction. Cellular metabolism is the sum of all chemical reactions occurring in a cell. Metabolic reactions usually occur in pathways or cycles. All cells perform catabolic and anabolic reactions. Rates of catabolism and anabolism must be carefully controlled. Breakdown or energy-releasing reactions, that's catabolic reactions, must occur at rates that balance with build-up energy-utilizing reactions, that's anabolism, and these rates are regulated by the presence of enzymes. Imbalances in reaction rates can damage or kill a cell. Different types of cells conduct specialized metabolic processes due to the enzymes they produce. So some processes like detoxification can occur in liver cells because liver cells produce enzymes that detoxify. Enzymes are used to control the rate of both catabolic and anabolic reactions, and they greatly increase reaction rates when present. When we talk about controlling the rate, if we don't want a reaction to occur, we can just remove the enzyme. The reaction could still occur, but it would be so slow that it doesn't really matter. A cofactor is a non-protein substance that binds with the enzyme to activate it. Some help fold the active site of the enzyme into its proper conformation. Some help bind the enzyme to a substrate. A cofactor could be an iron, an element like minerals, the minerals that you are required to consume in your diet, or small organic molecules known as coenzymes. Coenzymes act as cofactors, and they are usually vitamins. That's why we need vitamins. They are essential organic molecules that we get from our diet so that we can properly produce particular enzymes. Denaturation occurs when proteins unfold and lose their 3D conformation. This is because of a change in the secondary or tertiary structure of a protein. The bonds holding the protein in its characteristic shape are broken so that the protein chain takes on a random, disorganized conformation. Denaturation can result when proteins are heated, including when the body temperature rises too high, or when proteins are subjected to extremes of pH. In some instances, denaturation is accomplished by coagulation or precipitation. Sometimes denaturation is reversible and other times irreversible. In the case of enzymes, irreversible denaturation stops it from functioning. For example, you cannot undo cooking an egg. Because the heat damages our enzymes and proteins, this is one of the many reasons that homeostasis maintains a narrow range of pH and body temperature. Nucleic acids are high molecular weight macromolecules responsible for storing and using genetic information in living cells and passing it on to future generations. They carry the genetic code in DNA, or they aid in protein synthesis with RNA. Nucleic acids encode amino acid sequences of proteins. The building blocks of nucleic acid are called nucleotides, which consist of a sugar, a phosphate group, and an organic base. DNA, or deoxyribonucleic acid, is a double chain of nucleotides, and RNA, or ribonucleic acid, is a single chain of nucleotides. Both types of nucleic acids are made up of nucleotides, which in turn are composed of 3 simple components. Each nucleotide contains a base, either adenine, uracil, cysteine, guanine, or thymine, and a sugar and a phosphate group. The 3 components are chemically bonded together with the sugar molecule lying between the base and the phosphate. In RNA, the sugar is ribose, whereas in DNA, the sugar is deoxyribose. When nucleotides bond together to form nucleic acid chains, the bonding is between the phosphate of one nucleotide and the sugar of another. The resulting nucleic acids consist of polynucleotide strands of alternating phosphate and sugar molecules, with the base molecule extending out of the strand from either sugar molecule. DNA takes the form of 2 strands that coil around each other to form a well-known double helix. Some RNA occurs in essentially straight chains, whereas other types could form some loops or helices. DNA stores our genetic code. It contains the sugar deoxyribose. It is a double-stranded helical molecule known as a double helix, and it's located within the nucleus of our cells. There are 46 linear strands of DNA in each cell nucleus, and each of these 46 strands is known as a chromosome. The bases of the nucleotides within DNA are adenine and guanine, cytosine and thymine. The bonding of nitrogenous base from one strand to the opposite strand is very specific. It follows complementary base pairing rules. Adenine always pairs with thymine, and cytosine always pairs with guanine. RNA is a single-stranded linear molecule, and it's active mostly outside the nucleus. It links DNA to protein synthesis and is slightly different from DNA. It contains a ribose sugar instead of deoxyribose, and while it's composed of nucleotides, there's no thymine. Instead, it is replaced with a uracil base. 3 varieties of RNA carry out the DNA orders for protein synthesis. They are messenger RNA, commonly represented as mRNA, transfer RNA, or tRNA, and ribosomal RNA, or rRNA. ATP, or adenosine triphosphate, is the main energy-carrying molecule in the cell. Energy from ATP breakdown is used for cellular work. Chemical energy is released when nutrients from food, that's the things that give us calories like carbohydrates, proteins, fats, and alcohol. For example, glucose, when you break down a glucose molecule, you break the bonds between the carbons of glucose. Energy is released and captured in ATP. ATP has 3 portions: adenine, ribose, and a 3-phosphate chain. It is the bonds between the 2nd and 3rd phosphate that take a lot of energy to make and release a lot of energy when they're broken. So breaking these bonds releases energy that can be quickly transferred to other molecules. ATP directly powers chemical reactions in cells. It offers immediate, usable energy needed by body cells, and it drives cellular work for transport, chemical reactions, mechanical work like contraction of muscles. If an ATP breaks off a phosphate to release energy, then it becomes ADP, adenosine diphosphate. And if we were to break off 2 phosphates, then it would become AMP, adenosine monophosphate. These are recycled though. They would just go back to where we're breaking down the food and releasing the energy and capture that energy by getting new phosphates put on it so that it becomes ATP again.